Topic of discussion today is RAN capacity planning in 5G. Okay, so these are the few objectives we want to cover in this session. So first of all, we'll see what are the IMT expectations for area capacity and the spectral efficiency in 5G. After that, we will discuss the effect of wider bandwidth carriers, carrier aggregation, and dual connectivity on capacity of a user. And after that, we will explore the effect of beamforming, MIMO, and the new radio air interface on the spectral efficiency. Lastly, we'll go through the transport as well. So in transport, we'll see how changes in 5G will help to improve the capacity, right? So these are the few topics we'll cover. We'll try to cover in this small session. Okay, so guys, so these are the topics we'll cover in this session. So first of all, we'll cover that what are the IMT 2020 expectations related to capacity. We'll also go through spectrum and bandwidth, how to improve our bandwidth and how it will affect our capacity. In addition to that, we'll talk about spectral efficiency, 5G RAN capacity, and the transport capacity. So these are the 5-6 topics we'll try to cover in this particular webinar. First of all, before jumping to session, we should know what is IMT and what is ITUR, because I will say these terms many times. So IMT is International Mobile Telecom, and ITU is the International Telecom Union for Radio Communication. So the main job of ITU is to set a benchmark for all the future mobile communication, and the result is IMT. IMT is International Mobile Telecom, or you can say 5G in simple terms for IMT 2020. So at a high level, you can say that IMT 2020 follows the same naming structure as in previous G. So for 3G, if you remember, we call it IMT 2000, right? For 3G, we call it IMT 2000. For 4G, we call it IMT Advanced. And for 5G, we are calling it IMT 2020, right? So for 3G, we call it IMT 2000. For 4G, we call it IMT Advanced, and for 5G, we call it IMT 2020. Okay. So ITU identifies 3 usage scenarios associated with 5G requirements. So in general, there can be various or several user cases, but the 3 usage scenario represents the cases with an extreme 5G requirement target. The first case you see here is the enhanced mobile broadband, or you can see EMBB. So it basically means more data to you as a consumer. So you can say that this is related to our capacity. So in this session, we'll talk about this a lot, EMBB, right? So you can say if you before took maybe a minute to download your movie, hello, in 5G, you can do that in few seconds. We know the demand for mobile broadband will continue to increase, leading to enhanced MBB. So the EMBB usage scenario will come with new application areas and requirements. In the end, it's all about seamless user experience. And this case, as I said, is related to capacity. There are 2 more cases, important cases, like ultra reliable low latency communication, which is also called URLLC. And the third one is massive machine type communication, or it is called MMTC. So we'll not talk about these 2 cases. We'll talk about only EMBB in this session. So these are the 5G technical use cases we are talking about. And think of it like a pyramid, and you can visualize all these 3 cases. Okay. So these are the 3 cases. So let's jump to the 5G capability, right? So according to ITU, 5G is expected to provide a user experience matching as far as possible fixed network. The enhancement will be realized by many factors like increased data rate, enhanced spectrum efficiency, reduced latency, all these kind of things. So in this spider chart, the key capabilities of IMT 2020 are shown as compared to IMT Advanced. As I told you earlier that IMT Advanced is 4G and IMT 2020 is 5G, right? So this light green, this represents 4G, and this dark green represents 5G, right? So let's see some of the important differences between 2 technologies, 4G and 5G. So first of all, you see that peak data rate. Peak data rate in case of 4G, it is around 1 Gbps, but now it is increased to 20 Gbps in case of 5G. Then we have spectrum efficiency. You can see in case of 4G, it was 1x and now it is increased to 3x. So 3 times capacity out of the same bandwidth. Okay, you can see the capacity increased by 3 times because our spectrum efficiency increased by 3 times. Then the most important thing is the area traffic capacity. You can see that in case of 4G, it was around 0.1 Mbps per square meter, right? But now it is increased to 10. So it is increased 100 times as compared to 4G. So we'll see why it is increased and what happens in 5G that capacity increase so much, right? So we talked about peak data rate, we talked about spectral efficiency, and we talked about area capacity. So these are the 3 things we'll talk about: how to increase or how to improve our spectrum efficiency, our area traffic capacity, peak data rate in this particular session. Okay, there are 8 capabilities. We'll not talk about these. There is improvement related to user experience data rate. There is improvement related to latency, connection density, network energy efficiency, mobility, but that is not topic of this session. So we'll talk about capacity on. Okay, so area capacity. So one way is to think of area capacity is to visualize it as a cuboid. So we have 3 axes. As you can see, we have x-axis, y-axis, and z-axis. So just visualize that in x-axis, we have bandwidth. In y-axis, we have spectral efficiency. And in z-axis, we have the cell density. So the area capacity, which we talked about, is 100 times as compared to 4G. So it is dependent on all these things. So if bandwidth is improved, then area capacity will be increased. If spectral efficiency is improved, again, area capacity will be improved. If cell density is improved, then area capacity will be improved. So it is a combination of these 3 things. If any of these 3 things will increase, area capacity throughput will improve, right? If all of these 3 improve, then you can think that yes, area capacity throughput will improve, right? And before going to the session, I just want to say, just remember these 2 formulas we'll talk about a lot. Capacity is equal to bandwidth log 1 plus sin R. So you know the Shannon laws. So this is the Shannon laws that capacity is dependent on the bandwidth. So if higher the bandwidth, capacity is very high. If higher the sin R, capacity will be very high. And second formula, always remember, spectral efficiency is equal to throughput divided by bandwidth. Okay. These 2 formulas you should always remember by heart, because these formulas helps us a lot in the telecom industry. That spectral efficiency dependent on throughput and bandwidth. So higher the spectral efficiency, higher the bandwidth, and higher the throughput. Okay. So next topic we have to go on through is spectrum and the bandwidth. Okay, let's talk about spectrum and the bandwidth. How we can increase the bandwidth? What are the various ways to increase the bandwidth? So in this slide, you can see there are 3 ways to improve the bandwidth. The first way is dual connect. As you know that 5G can work in 2 ways. One is NSA, which is non-standalone mode, and second one is SA, which is standalone. In case of SA, it will be end-to-end 5G, right? End-to-end 5G, like core is of 5G, transport is of 5G, RAN is of 5G, and everything is of 5G. But in case of NSA, the UE is connected both to LTE as well as 5G, right? So this is NSA. So with the help of NSA, our bandwidth can be improved. So suppose our master node MN is having bandwidth of suppose 20 megahertz, and suppose our G node B secondary node has bandwidth of 100 megahertz, just suppose, then UE will get benefit of total 120 megahertz, right? So this way our bandwidth will be improved in case of NSA mode, or you can say dual connectivity mode. The second thing is wider bandwidth carrier. As you know that 5G can work in 2 frequencies. One is FR1 and one is FR. For FR1, it is between 400 megahertz to 7 gigahertz, and FR2 is between 24.2 gigahertz to 52.6 gigahertz. right? For FR1, maximum bandwidth can go up to 100 megahertz. And for FR2, it can go to 400 megahertz. Some documents say it can go up to 800 megahertz, 1200 megahertz, but at this moment, just think of 400 megahertz. So in case of LTE, our bandwidth maximum is 20 megahertz, but now it increased to 400 megahertz. So you can see 20 times bandwidth as compared to LTE, right? So this shows the improvement, right? So this is the second way to improve the bandwidth in case of 5G. The third way is the carrier aggregation. So carrier aggregation is same in 5G as in 4G. So carrier aggregation is a technique to boost data speeds. It involves adding multiple carriers simultaneously to create a wider channel for data transfer. So consequently, this results in the increased data throughput. So these are the three main mechanisms used to increase the bandwidth. One is dual connectivity. Second one is wider bandwidth carriers, and third one is the carrier aggregation. As far as carrier aggregation is concerned, you see that in case of 4G, our maximum channel bandwidth is 20 megahertz. And how many carriers can be aggregated in case of 5G? In case of 4G, these are 5. So how much is the maximum bandwidth we can get in case of 4G? That is 100 megahertz. Right? That is a huge amount at that time, but not anymore. But in case of 5G, as we have discussed, that maximum bandwidth can go up to 400 megahertz. And how many carriers can be aggregated? Maximum 8 carriers can be aggregated. In new releases, it's written that 16 carriers can be aggregated, 32 carriers can be aggregated. But at this moment, just think of 8 carriers. Just think that 8 carriers can be aggregated. So 8 carriers can be aggregated. Then how much is the total bandwidth we'll get? We'll get around 3200 megahertz, right? So you can see we have improvement of 32 times as compared to 4G. Yes, this is a theoretical improvement, but just think in case of theory. Practically, there may be some losses and some other things, but just think that it increased from 100 megahertz to 3200 megahertz, 32 times as compared to 4G. Right? So when we talk about bandwidth, we have to talk about spectrum available for 5G as well. As I said earlier, that 5G can work in 3 bands. One is low band, one is mid band, and the last one is the high band, right? So first one is low band. So low band is available for 4G communication as well. In 5G, we are adding one more band, which is mid band. Here we can have this, what you call 3.5 to 4.2 gigahertz as well, right? Which is our C band, DoD band, or CBRS band, right? And also in this band, we are adding the unlicensed spectrum as well, right? So, and then in addition to that, we have high band as well, which I told you between 24.2 gigahertz to 52.6 gigahertz, right? So we have first low bands, mid bands, and high bands. As you know that the propagation of low band is highest as compared to mid band and high band, right? But the bandwidth of low band is very low. It can be between 10 to 20 megahertz. In mid band, it can be 50 to 100 megahertz. In case of high band, it can be between 400 to 1200 megahertz, right? So bandwidth increases. So as we go from low band to high band, we have more available bandwidth, right? But there is always a trade-off, or you can say balancing we engineers do. Higher the frequency, lower, or you can say smaller the propagation of that frequencies, right? So you can see here cell radius, right? So cell radius is very large in low band as comparison to the high band, right? Then penetration loss. So penetration loss may be proportional to the thickness of the wall or glass. In 5G, or you can say in case of millimeter waves, if we have 5 millimeter glass, then there will be loss of around 4 dB, which is a big loss. If we have a 10 millimeter glass, then there can be loss of around 8 dB, right? So this is a big loss. So in case of low band, there is not a much issues related to in-building penetration, but high band, there is a big loss, right? And mid band is in sweet middle path here. We can take advantage of both low band as high band. And what about bandwidth? As I told, bandwidth is very less in case of low band, but it's very high in case of high band, right? And low band can work only in the FDD, but mid band and high band can use both FDD, TDD as well. And high band, generally we work on TDD only. Okay. And data rates are very high in high band as compared to the low band. Okay. So in addition to millimeter waves, there is one more thing why 5G capacity is more as compared to 4G. So in this slide, we'll see one more way to have higher, or you can say wider bandwidth. So you can see that in 4G, 5 carriers can be aggregated with the help of carrier aggregation, right? So we thought that our maximum bandwidth can go to 100 megahertz, right? But that is wrong, right? You can see that after every carrier, there is a guard band, right? There is some guard band of around 2 megahertz, right? So our net bandwidth we get after carrier aggregation in case of LTE is what you call 90 megahertz, right? 18 plus 18 plus 18 plus 18 plus 18, we get 19 megahertz of bandwidth, right? Net bandwidth we get in case of 4G is 90 megahertz. But in case of 5G, we have single 100 megahertz carrier, right? So yes, we have guard band required in case of 5G as well, but on the extreme ends, on the left, there is some guard band required, on the right, some guard band required. So in case of 5G, our net bandwidth is 98 megahertz. Here in LTE it is 90 megahertz, and you can say here it is 9. There is loss of around 10% in case of 4G, but there is loss of around just 2% in case of 5G, right? So these are the things we should also remember, that why bandwidth is higher in 5G as compared to LTE. Okay. Then we have split bearer or the non-standalone mode, right? So this is also called PDCP aggregation. We'll talk about this in detail in next few slides, but this is also called PDCP agree. This is not carrier aggregation, right? So you can see that they have two modes. So first of all, data coming from core, and some data go to master node, maybe it is E node B, and some data goes through G node B, right? So that's why we take the advantage of bandwidth of E node B as well as G node B. And as we discussed, then the bandwidth of UE will be high, right? So this is our PDCP aggregation, or you can say split bearer, right? With the help of split bearer, our bandwidth can be improved. Okay. So we have discussed about bandwidth, how to improve the bandwidth, and with the help of bandwidth, our area capacity throughput will be increased. So you see here, bandwidth plays a significant role in increasing the area capacity, right? So first part is discussed, right? Then I said that in 5G, we have some new spectrum. FR is between 450 megahertz to 7000 megahertz, and FR2 is between 24.2 gigahertz to 52.6 gigahertz. You can see here for FR1, the cell size, right? You can see here the cell size is very big, right? You can see this area can be covered with the help of only 3 sites or 3 cells, right? You can see as we go towards FR2, or as we go towards the millimeter waves, the propagation distance is very high. Propagation distance is very low, and the attenuation is very, very high. So this small area can be covered by these amount of sectors, right? Here only 3 sectors in case of FR1, but here maybe 20-25 sectors for covering this small area. So in case of millimeter waves, we have force. It forces us to increase the density of cells, right? So it forces increase density of cells, right? So in case of FR2, we need more sites as compared to FR1 to cover the small area. So this part is covered. So cell density is more in case of 5G as compared to LTE, right? Because you know that lambda or wavelength is equal to or directly proportional to 1 divided by frequency. higher the frequency, lower the wavelength. Lower the wavelength, higher the frequency, right? So here, in case of FR1, frequency is low and wavelength is high. And here, in case of millimeter waves, frequency is high, but wavelength is low, right? So this is the second part, which is the cell density, right? The next part is spectral efficiency. So as we have discussed that IMT 2020 has said that we have spectral efficiency 3 times as compared to 4G, right? 3 times as compared to 4G, right? So how to get that extra spectral efficiency? So we'll see in next couple of slides how to get that extra spectral efficiency, right? So let's begin. So before jumping to that spectral efficiency, let's see if people have any question. Okay. So guys, before jumping to the spectral efficiency, any questions? Can you please write in the chat box if you have any question? In the meanwhile, I will take a sip of water. Okay. No questions. It means, so can you write yes in the chat box if you are getting what I'm saying? Please write yes in the chat box. Okay. Thank you. Okay. Let's begin. Let's talk about some of the ways of increasing spectral efficiency. So there are 4 ways. We'll talk in detail. So the first way is time division duplexing, or you can say TDD. So in case of TDD, time rather than frequency is used to separate the transmission and the reception of the signals. So here, a single frequency is assigned to a user for both directions. The more efficient we are, the better area capacity we can achieve, right? Then we have this new radio channels and signals. In case of 5G, we have very less overhead as compared to 4G. So we'll talk about these these reference signals in next few slides. Then we have this MIMO, right? So in case of 5G, we can do 4x4 MIMO, 8x8 MIMO, or whatever, right? So this allows my time and frequency reuse for my bandwidth 4 times within that, right? Within that cell, right? So it is frequency reuse concept. So if I have 10 megahertz of spectrum, it is actually 40 megahertz of spectrum. So you can see then my bits per second per hertz will improve dramatically, right? So, and one of the enablers for that is the beamforming. Yes, beamforming is there in LTE as well, but it is very limited in case of LTE because beamforming is dependent on the number of antenna elements, and antenna elements is dependent on the frequency. In case of LTE, our frequency is very small, so bandwidth is very large, so antenna elements are very large, so it may not be that possible beamforming in case of 4G. So here in 5G, every cell is beamformed from the day one. So beamforming is the foundation of 5G air internet. So these are the 4 ways by which spectral efficiency can be improved. So let's go through these 4 ways in detail. So first way is TDD, right? So as I said, 5G NR support both FDD as well as TDD, right? So in FDD, what happens? FDD has different carrier for uplink as well as downlink. But TDD has one carrier shared in time between uplink and the downlink, right? So as you know that in 5G, we have something called slots, right? So if you want to get more information about slots, please go through that 5G NR frame structure. In that, I have mentioned frame slot in too much detail. It is more than like 1 hour session. So please go through that video. So in slots, you know that we have 14 symbols, right? We have 14. So in case of 5G or in case of TD, some symbols can be downlink and some symbols can be uplink depending on the requirement. So if downlink throughput requirement is more, then we will assign more symbols to downlink. If uplink requirements are more, then we will assign more symbol to uplink. So it is also called dynamic TDD in case of 5G. Okay. And as I said earlier, in millimeter waves, we expect TDD because it is unpaired. So up in the frequency, more of the spectrum is TDD, right? So here in TDD, a single frequency is assigned to a user for both directions. The more efficient we are, the better area capacity we can achieve. In FDD, one carrier is used for downlink and other carrier is used for uplink, right? So 2 carriers, right? But you can see that in case of FDD, DL and UL is always 50-50. right? Suppose DL is very loaded, right? Suppose DL is very loaded, right? Then we may have potential unused uplink, right? In case of FDD, right? So if it is already very loaded, then we may not use uplink to the full extent, right? But in case of TDD, DL and UL are fully configurable, right? So we can use as 70-30, we can use as 30-70, we can use as 50-50, whatever according to the situation, right? That's why it is called dynamic. So if I run out of capacity in downlink, then I will use unused capacity on this uplink carrier. So it is less wastage of bandwidth in case of TDD. So in TDD, it is divided in time. Part of time is downlink and part of it is uplink, right? So as I said earlier, in TDD, uplink is separated from downlink by the allocation of different time slots in same frequency band. So 5G NR uses TDD very dynamically. So as I said, one slot has 14 symbols. Inside the slot, a given OFDM symbol can be uplink, downlink, or flexible symbol. This F is a flexible. So a flexible symbol can either be uplink or downlink symbol as needed. You can see there are 62 slot format defined in case of 5G, but there is no such 62 slots in case of 4G. They are just 6 options we have. But here we have 62 options in case of 5G. So in 5G network, we can switch from one format to other as needed according to our requirement. If we require more uplink throughput, then maybe we can use this maybe 34, right? Maybe this 34 option. If we require more downlink, then maybe we can use this third option, second option, depending on the requirement, right? So that's why it is called the dynamic TDD or full TDD, right? So this is all about TDD. So with the help of TDD, our spectral efficiency will be improved because there is no wastage related to the bandwidth, or you can say very less wastage. Never use the word no in case of telecom. There must be some trade-in here and there, but yes, you can say there is less wastage as compared to 4G, right? Then we have MIMO. So what is MIMO? As you know that MIMO is massive input, massive output, right? So if you see here, 4x4 MIMO, and this is, I'm talking about what you call single user. So 4x4 MIMO means I'm using time frequency resources 4 times. Suppose I have 10 megahertz, it means theoretically I have around 40 megahertz, right? Around 40 megahertz. So 4x4 MIMO means I am using time frequency resources 4 times. 2x2 MIMO means 2 times, and no MIMO means I'm using only 10 megahertz, right? But what's the problem with MIMO or single user MIMO is that it is limited by UE RF conditions. So what happens? So if UE is in good RF conditions, then 4x4 MIMO is possible. That is not a big deal. But if it is in the less good RF conditions, then we can go to 2x2 MIMO. But if RSRP is very low, then there will not be any MIMO. So in case of bad RF conditions, MIMO can't be used and there will not be any improvement related to bandwidth, right? So MIMO or single user MIMO is useful in the good RF condition, right? So this is the disadvantage, but advantage is that when we have good RF condition, our bandwidth can be improved, right? Then we have multi-user MIMO. Let's see how it works. Suppose UE is not in good RF condition, right? So not in good RF conditions, we can't do 2x2 MIMO, we can't do 4x4 MIMO. Since I can use the time frequency resources in different beam, so I can use 4 layers of MIMO even if used in the bad conditions. So that is cell capacity thing. You can see I can use 4 layers of MIMO even if the UE is in the bad conditions, right? So this is the biggest advantage of massive MIMO or multi-user MIMO. Even in our bad conditions, our capacity will be improved. But yes, if this UE is in a good condition, it will be improved 16 times because we are using 4x4 MIMO, right? It will be increased 16 times, 4 times here and 4 times in the beams. So 16 times. But If the U is in the bad conditions, even then it will be improved at least up to 4 times in case of massive MIMO, right? So that's it. If they are in good condition, they can do 4x4 MIMO each, right? So I can take time frequency resources will be 16 times if we are in the good RF condition, right? Obviously, it depends on vendors and many other conditions, but that is the use, right? And you can see that normal MIMO or 2x2 antennas can be used in the wide areas or in the farms or in the village. And this medium capacity can be used in the good cities or highly populated cities. And this massive MIMO is very useful in the hotspots, right? You can see in the stadiums or in the high populated area, right? So these things we can use. So each multi-user MIMO can do up to 4x4 MIMO, right? So this is the basic advantage of this massive MIMO, that it can improve our capacity or spectral efficiency even we are in the poor RF condition, right? Next topic is beamforming. Let's see, someone has pinged some. So massive MIMO is not clear. This is what you are saying. Okay, let's talk about it again in detail a little bit. Let me. Okay, so let's talk about. Suppose I have one antenna. I have one UE. UE. I have three UE. Okay, I have three UE. UE1, UE2, and UE3. Right. And suppose I have three resource blocks. Right. So suppose I have like 100% of resources. So you can see that in case of normal MIMO, right? In case of normal MIMO, maybe 20% of resources goes to UE1, right? Maybe 30% of resources goes to UE2, and maybe 50% of the resources goes to UE3, right? So this way we can improve our bandwidth and we can improve our capacity, right? But in case of massive MIMO, what happens is that the whole 100% of the resources is given to UE1, UE2, and UE3 if they are specially like if they are space apart. There should be some distance between this UE1, UE2. So all these resources are given to all these three UEs. So you can see that capacity is improved by 3 times as compared to normal MIMO. So here, these resources are separated and they are divided between three UEs. But these 100% resources are given to all three UEs. So capacity is improved by 3 times. This is what I want to say, that 100% of resources are given to all the users if they are separated by particular distance. So this is the effect of massive MIMO, or this is the improvement of massive MIMO as compared to the normal MIMO. This is what I want to say. Okay. Okay. Thank you. Yeah, it's multi-user MIMO. Yeah. Okay. Let's talk about massive MIMO and beamforming a little bit more. So, what are the benefits of massive MIMO? So, our throughput will increase to the user via MIMO and carry aggregation with high pod counter antenna. And beamforming increases signal to UE and reduces interference to other UEs. Let's talk how they do it. So, what are the few 5G RAN challenges we are facing nowadays in case of 5G? So, in 5G, we have not in 5G, you can say, but in our normal life also. Nowadays, there is high demand of throughput. There is high demand of throughput. Every user want good experience and we want coverage everywhere, even in our basement, right? We have to utilize spectrum in better way, right? And we have different cases related to urban, suburban, rural. So we have different kinds of antennas for urban, different kinds of configuration for suburban, and different kinds of radios for rural. And nowadays, revenue is very less as compared to data uses. The moment we are free, even for single second, just observe your day from now onwards. Whenever you are free or whenever you're alone for a single second, you pick your phone and you start doing some whatever on the data, right? So data rate or data use are increasing at a faster rate. But not is related to this 5G. I want to say one thing, that whenever you are free, right, don't pick your phone or don't pick your iPad immediately. Just think, just do meditation, just think what's your plan to improve your capabilities, to improve your what you call performance, or what you can do to have uh, more progress in your life, right? Don't I You can see if you pick my phone, I don't use phone or any digital devices for a long time. I pick up only when it is required. So just think, whenever you're picking the phone, why you are picking this phone? Is it something urgent, or then don't pick? Just unnecessary scrolling of mobile phone is not used. It affects your brain. You can see my videos related to subconscious mind and how to start your day. Very nice videos, and lots of views are there. Just see those videos and you will see that it will help you to progress in your career. Okay. So you can see that we have three types of beams. One is omnidirectional, one is sectorization, and one is beamforming. So in early days of cellular system, we have omnidirectional use, right? So one antenna cover all the direction, right? When more capacity is needed, cell split was done. That is splitting the omni cells into three or more sectors. Therefore, the capacity will be increased manifold. But to increase capacity even more, smaller areas can be covered with the help of these narrow beams. To this, we need a large antenna arrays like massive MIMO, or at least uncorrelated antenna elements, and that is called beam forming, right? So in order to understand beam forming better, we need to recap a little of basic multi-antenna and radio channel theory. So you can see that there are two types of processes or interference. One is constructive interference and one is destructive interference, right? So constructive interference is a way of adding two waves together to maximize the amplitude power of resulting waveform. You can see that we have two waves. One is wave 1 and other is wave 2. So you can see there may be some amplitude for this. You can see there may be some amplitude for this. There may be some amplitude for this. And with the help of this constructive interference, our amplitude is increased twice, right? So if it is A, it is also A, then it is here 2A, right? But in case of destructive interference, you can see that here we have some amplitude and we have some amplitude, and you can see there is no amplitude, right? This is the destructive interference. So destructive interference, when adding waves out of phase, will do the opposite. It will decrease the amplitude and the power of the resulting wave, right? So that's why when amplitude is improved, our signer will improve. When our signer is improved, our capacity will improve. So you can see here that if the waves transmitted by two antennas are emitted in phase, right? This is phase, in phase, there will be constructive interference in the forward direction, and it will generate a peak in the antenna diagram. And moving away from the symmetry axis, we will see destructive interference generating a null, right? So suppose our UE is here, right? And there is no UE is here. Then why to waste our energy? So the place where there is no UE, no signals. The place where we have UE, all the power in that direction. So in this way, our signer will improve because there will be less interference in the direction where there is no UE, and there is high constructive signal energy, the location in which UE is there, right? So this way we can improve our signal energy, right? This way we can improve our signal energy and our signer will be improved, right? So this is what I was talking about in beam forming, that when they are in phase, you can say that I am maximizing the energy in the given direction by modifying the amplitude and the phase of my two symbols in my two antenna elements, right? I'm maximize my signal. You can see that I'm A plus A is equal to 2A, right? And you can also say that I minimize my interference in other way, in other places where there is no UE, right? And with the help of beam forming, our power is increased to 4A square. That is a huge increase, right? So earlier it may be A square, but now it is power is increased up to 4A square, right? You remember that when you were a child, with the help of magnifying glass and with the help of sunlight, you are able to burn a paper, right? Because why you are able to burn the paper? Because you are able to focus that energy in that particular direction. Same thing with the help of beam forming, all the energies is focused on this particular UE. With the help of that, our power is increased. And in telecom, everything is power. More the power in a particular direction, more the capacity we have, more the signer we have, more the spectral efficiency we have. So all these things are dependent on the power, or you can say all the things dependent on the less loss of power, right? Interference is loss of power, signal is gain of power, right? So with the help of beamforming, we can get lots of gain in signals, right? So you can see that in 5G, we can create beam within the sector coverage. You can see that in case of LTE, right? This is our sector, right? This is our sector. So you can see that it covers lots of area, but you can see the propagation is very less, right? In case of 5G, you can see propagation is up to here, but in case of LTE, propagation is only up to here, right? So when we create beams, we increase the signal strength in the direction of user, and outside of the beam area, we are reducing the interference, right? So you can see that in case of 5G, we use various kinds of modulation schemes like BPSK, QPSK, 16 QAM, 64 QAM, 256 QAM. When UE is in the good conditions, we can use 256 QAM. And when we use higher modulation, our SINR is very high, because in that case, our interference plus noise ratio is very low, right? You can see that when U is in the bad conditions, we can have bit efficiency of 2 bits, right? We can use 2 bits per resource element, right? So here in QPSK, our bit efficiency is, you can say, our bit efficiency is 2, right? In case of 16 QAM, our bit efficiency is 4 bits, right? So here we can use 4 bits per resource element. You can see that our spectral efficiency increased like 100 times as we move from QPSK to 16 QAM. Here we have 2 bits, here we have 4 bits. So our spectral efficiency increased twice. If we increase from 4 bits to 6 bits, again, it increased around 50%. And from 6 bits to 8 bits, again around whatever. So it increased two more bits, right? So you can see that as we move towards higher modulation, our bit efficiency improves, and higher the bit efficiency, higher the SINR. And this bit efficiency is improved because our signal strength is improved. And since signal strength is improved, our SINR is improved, and then our bit efficiency is improved. So all these things are interrelated: SINR, bit efficiency, increased signal strength. So if one is improved, then other things will be impacted, right? So all these things are related to each other. So this is the effect of beamforming on the signal strength and the spectral efficiency. Okay, so this we have discussed. So massive MIMO can help to improve our capacity, coverage, and the data rate, right? And massive MIMO means multiple input, multiple output. And in case of massive MIMO, we are using large number of antennas. It can be 64, 128, 16, and so on. And beamforming in massive MIMO focus signal energy towards specific user devices, and it will increase the signal strength and reducing interference from other uses or the devices, due to which our SINR will. In case of spatial multiplexing, we have transmit multiple data streams simultaneously over the frequency band, and this increases the network capacity. And also, as I said, enhanced coverage, because we can focus our signals for a long propagation distance, right? So in MIMO, in case of enhanced coverage, the coverage of network is improved due to ability of antennas to focus signal energy in the specific direction, right? This allows better signal quality, right? So this is all about massive MIMO and the beamforming, and it helps to improve the capacity, coverage, and the data rates, right? And these are the essential techniques for better connectivity and the super user experience. Okay. And again, before moving next section, I request everybody, please give me your comments in the comment box, and please give me answer to these questions. Is this video useful to you? And what is the topic of next video you want to watch? And this will be very helpful to me to grow the channel. Okay, so please answer these 2 questions in the comment box. So these are the 4 ways. So till now we have discussed TDD, we have discussed massive MIMO, we have discussed beamforming. So with the help of these 3 ways, we can improve our spectral efficiency. And before moving to this NR channel and signals, or you can say overhead. So any questions so far, please let me know. Okay, let's move to our next topic, which is new radio channels and the signals. So the reference signals in 5G NR are different from LTE. In LTE, if you remember, we call it CRS, or you can say cell reference signals. In 5G, we call it CSIRS along with plus demodulated reference signal. So in LTE, these cell specific reference signals are always enabled. They cause most of the downlink interference. But in 5G, such reference signals are removed, and reference signals are only used when UE has data allocation. Basically, they are more like UE specific reference signals. So here, in case of 5G, they are UE specific, but here in case of 4G, they are always enabled, even if it is not required. Right? So this kind of structure will reduce the downlink interference. Consequently, it will improve the channel quality, resulting in the better spectral efficiency and the capacity. So long story short, CSIRS is configured per device rather than a cell. In LTE, we have CRS. It is transmitted continuously and it is based on the site and they are kind of overhead. So depending on type of MIMO, 2x2 MIMO, 4x4 MIMO we want to do, that amount of overhead will increase significantly. So in 5G, we have CSIRS. So in 5G, this overhead depends on the device uses. So if my mobile can't do MIMO, then no overhead, right? So in 5G, CSIRS is configurable per user, right? You can see it can be semi-persistence, like when they are not available all the time, or it can be on demand. So it can be based on demand. Then we have this PDCCH. If you remember, in case of 4G, we have maximum 3 PDCs assigned, right? That is same in 4G, in 5G as well. Maximum 3 PDCs can be, 3 PDCS symbols can be assigned out of this 14 symbols, right? But what is the difference? So in case of 4G, all these subcarriers should be used for PDCCH, right? In case of LT, right? All the subcarriers should be used in case of LT. What change we see in case of 5G? So in case of 5G, instead of using all these, we can use this amount of resources, right? So in 4G, we have to use all subcarriers, but in case of 5G, we can use these amount of resource elements. So we can save these amount of resource elements in case of 5G. So I can use this amount of resource elements because I do not have lots of signaling overhead, right? So this is the difference between PDCCH LTE and PDCCH 5G. Okay. Then we have this PDSCH and PUSCH. As you know that this SCH is the sharing channel, downlink sharing channel, and U means uplink sharing channel, and these are used for data transfer, actual data transfer, and this PDCCS is used for signaling, right? This maybe you remember from the LT, right? So PDSCH and PUSCH. So we can multiplex user during a transmission time interval in case of 5G. Suppose I have a sensor, suppose I have a sensor which needs very less data to communicate, right? Then I can use this part of transmission for user one. Suppose I can use this part of transmission for user one, right? Then I thought even user number 2 doesn't need much data. Then I will give this to user 2. I will give this amount of resource element to user 2, right? So in 4G, we do not have that option. In 4G, a user get resources of complete resource block, right? So in 5G, we have much more flexibility and less overhead, which leads to improvement in the spectral efficiency, right? So these are the 4 ways with the help of which we can improve our spectral efficiency. Can you write in the chat box what are the 4 spectral efficiency ways we have discussed so far? And I will take a sip of water. So please write the 4 ways which we have discussed so far in the chat box. Good, beautiful. Okay, wow, all 4 methods are written. It means you are following this training. Thanks a lot for paying all the attention, guys. Thanks a lot. Good, Bhavesh, for writing all this in the fun line. Good. Thank you, Parvat, Pradeep, and other guys. Okay, thank you. So we have discussed these 4 ways to improve our spectral efficiency, right? And before jumping to the next section, the next section is 5G RAN capacity, right? So we have discussed 2 things in our previous slides. One is carrier aggregation and one is dual connectivity, or you can say PDCP aggregation, right? So first of all is the carrier aggregation. So in CA, you can see that there is a base station. It can be G node B or E node B. Let me change the color. This orange is not that visible. Okay. So in this particular example, we have G node B because we have this SDAP, and as you know that SDAP is 5G protocol. So right. So like in LTE, we also support carrier aggregation even in 5G. But the point is how CA and dual connectivity are different. So now what actually we do here is that, so all the packets, maybe packet 1, packet 2, packet 3, packet 4, come up to the MAC layer, and it knows two carriers, carrier 1 and the carrier 2. So MAC is responsible for scheduling, or you can say scheduler works at the MAC layer. So how to manage my radio resources? This is done by MAC. So all the packets come up to the MAC layer. So based on the load balancing or RSRP measurement, etc., I'm going to put onto two different carriers, carrier 1 and the carriers 2, right? And then we will put onto my subscriber. This way, my bandwidth is increased, right? So this is called the carrier aggregation, right? So this is simple carrier aggregation, and that is fine. But this we all know. So let's talk about dual connectivity. So in dual connectivity, we have one master node and we have one secondary node. So assuming both are G node B in this presentation, so we are showing just for simplicity. So what happens is that, so here I'm going to send packets from the master node, because master node is managing everything. That's why it's called master node. So you can see here SDAP is providing certain amount of quality of services, and PDCP also is there. So now this PDCP, after doing that ROHC, Robert Header compression, it is going to send RLC MAC. You can see RLC, it is divided at the RLC, right? RLC MAC, some to here and some to here, right? And this is also called what you call as forward tunnel, right? So having said, so packet will come through this forwarding tunnel to our MAC, RLC, and the physical layer. But what's the difference between carrier aggregation and the dual connectivity? The main difference is that here you can see that we have two schedulers. My friends, just see this, pay attention. Here we have two schedulers, but in case of carrier aggregation, we have only one scheduler, right? So if I say scheduler 1 here and scheduler 2 here, right? So there are two different schedulers. So one scheduler is the master node and other scheduler is the secondary node, right? So they are going to actually take some different sets of measurements from UE. And UE is the dual connectivity capable, and it is going to send the packets, different packets from different schedulers. Obviously, different radio carriers, right? So this could be C1 and this could be C2. So this is a fundamental difference. So when the dual connectivity comes into pictures, we have two schedulers. But if you left in the left side, carrier aggregation, we have only one scheduler. Okay. Now the question comes, is the low frequency better or the higher frequency better? So well, it depends. Lower frequency is good for providing coverage, while higher frequencies are good for providing capacity and the higher throughput. So let's talk about implications of deploying network in the low, medium, or the high band spectrum. So first of all, in low band, when we deploy in low band, we are going to get pretty good coverage. In this, the spectrum, the actual frequency wave is pretty long. So therefore, it propagates pretty well and it penetrates building pretty well, right? So this is the low band. Now, if I deploy in the mid band, since my spectrum is little smaller, the propagation isn't as good as in low band. Therefore, my coverage will be little less, and therefore I will need more towers or small cells to do that. However, I get an advantage because I can deploy and leverage more antenna elements. And in certain mid-band ranges, I can begin to use something like 64 different antenna elements, right? And this gives me unique advantage. And then we have high band. So when we go to the high band, notice that my carriers are very large because there is much more spectrum available there. I may have 100 megahertz or 400 megahertz carriers. That is where the highest size of carrier defined in 5G versus 4G. In 4G, we have just 20 megahertz. right? But downside here is like it propagates a lot less, therefore I will need more small. So now having said that, let's talk about capacity, overall capacity improvements. Now again, I'm going to provide some rough numbers to give you an idea, but these can vary depending on several other factors. First of all, I am deploying 5G in the low band. I can expect to get somewhere between 10 to 20% improvement. So there are some new things we can do in 5G, some new coding techniques and few other things that allow me to gain, but that gain is 10 to 20%. The improvement, by the way, is over 4G LTE, right? Sorry, just to be clear, that improvement is over 4G. When I look to deploy in mid-band, because I'm using a lower mode spectrum, I can have higher, large RF carriers, and I can get 2 to 4 times capacity improvement as compared to 4G. Right? And then finally, in the high band, I can get maybe 10 times capacity improvement as compared to 4G. And again, it depends on how many bands I'm aggregating, and it depends on how large those bands are. But clearly, to achieve this higher capacity, I want to use more spectrum, and more of that spectrum is available in the high band area. And we also have C band. So in C band, we also have extra bandwidth like 280 megahertz and 150 megahertz. Right? And C band is very helpful because it is good for coverage and capacity both and all these things, right? But it is more in the US, so we have to talk about in like pan world. So it will help it to improve our capacity. The last point we have to discuss is the transport capacity, right? So let's talk about RAN evolution to 5G. If you remember, in earlier like 10-15 years back, we have one core network and we have BBU. BBU is on the site, right? BBU on the site, and then it is connected to RU, right? So we have one BBU for each site, right? Then in LT comes a new configuration in which BBU is at a centralized site. So BBU at maybe at hotel or some room, and this BBU is connected to many sites, right? And it is also called CRAN, or you can say a centralized RAN. And after that, in 5G, it comes a new thing that this BBU is divided into two things. One is CU and one is DU. So lower layer goes to DU and higher layer goes to CU, right? So these are the differences between earlier LTE with CRAN and 5G RAN. So we'll see in next slides what is the advantage of this split of lower protocol layers and higher protocol layers. But this is how we grow from lower to higher, right? What is the advantage of this split? So first of all, this is one link here. So you can use that link to go through this complete detail. So yes, it will. So what is the advantage of this split? So yes, it will reduce the latency. There is no doubt about it. But what is the advantage in terms of capacity improvement? As we know, we need transport to transfer data. So what is difficult in 5G? So one of the main difficulties is that because of massive MIMO radios, the front haul capacity increase may be higher than 100 Gbps. You can see that front haul capacity is very high. Right now it's written 236 Gbps. This is unpractical to implement for point-to-point fiber links and a massive challenge for front haul networks. So with the higher number of antennas and radios and increase NR carrier bandwidth, a required front haul capacity increases proportionally. So this translates to many fibers or wavelengths in a high capacity CPRI capable optical system between RU and the bandwidth and the baseband. So in short, a split used in CPRI is causing a large increase in bitrate with large number of antenna elements in the 5G radios. Therefore, a different lower split is needed, right? So here you can see we need transport resources for 236 Gbps, but here we need transport resources of just 3 Gbps. So what an increase. So it will improve our capacity.